Now we're going to talk about inferential statistics, which are those tests that allow you to answer the question, this is what I found in this sample. How likely is it to exist in the population of all students? For example, this is what I found in my 10th graders when I used 2 different writing approaches. How likely is that to exist if we did this with all 10th graders in writing classes? Big question that you need to think about in this section is whether to use parametric or non-parametric tests, statistics, to see if your groups differ. You will use parametric tests if the scores are likely to be normally distributed in the population that your sample came from. Not your own sample, but the population of all 10th graders or all kindergarten kids. Think bell-shaped curve. So if your scores are likely to fall along a bell-shaped curve, you'd use parametric. A good example are scores on a reading test. On the other hand, you'd use non-parametric if the score distribution will deviate significantly from that bell-shaped curve in the population. So an example is 6 traits ranking or attitude surveys. Let's talk about inferential statistics for continuous data. Remember, continuous data are things like scores on a reading test, where you have an equal interval between each number. So when you would use it, if you have 2 different groups, which is what many of you will be doing, a treatment group compared to a control group, and your scores are normally distributed, you'd use an independent samples t-test. So if you're looking at pre-tests and post-tests on oral reading fluency, or on the NWEA or the MCA, things like that, you would use an independent samples t-test. On the other hand, you may have done an attitude or a motivation survey with your students also, and in that case a Mann-Whitney would be more appropriate. That's non-parametric because the scores are not normally distributed. If you have one group where you tested them twice, so for example you're doing a single subject design with 5 to 10 kids and you want to use statistics, you may not be using statistics with them. You may only be graphically demonstrating their pre to post test. But if you wanted to show gain from pre to post, a one sample t-test is what you would use for parametric statistics. If you have 2 groups that are matched, for example, if you had 2 classrooms and every other low student you put in a treatment 1 versus a treatment 2, every other medium student you did the same, you'd use a paired samples t-test, or for non-parametric, a Wilcoxon paired test. When you have 2 or more groups that are different at pre-test, so let's say you're working with 2 different second grade classes, and one has many more ELL or low achieving kids in it, your pre-tests are going to be at different levels, and for that you will use an ANCOVA, an analysis of covariance, where the test will equalize the beginning scores, vary it against the ending. If you have 3 or more groups, as in say there are 3 different kindergarten classes or second grade classes, and you want to see the effects of 3 different approaches to reading or writing, you would use an ANOVA. Keep in mind that you don't have to remember all that's on this slide. I want you to just look at it and think about it so that when we work with you to decide which is most appropriate, you'll have some idea of that. And you should at this point be thinking about which might fit for your data. These are for continuous data. Now, you may have categorical data. Remember, categorical data is pass-fail or low income, higher income, or 3 different levels. It's like ranks. And so in that case, you see here the different tests that you would use depending on whether the scores in the population are normally distributed or the scores in the population are not normally distributed. Again, just keep this as a reference so that when you have collected your data and thought about how you're going to analyze it, we can discuss which is most appropriate. Here I want to show you the inferential statistics that I used for my study of whether there was a difference in reading achievement for boys compared to girls. You'll remember that I showed part of this as the demographics back in the descriptives part of this presentation. And for the boys, the average was at the 62nd percentile on a reading test. For girls, it was the 64th percentile. Not much difference there. You can also see that their standard deviations overlapped a great deal, and therefore it was no surprise to me when the t-test was not significant. It indicated there was no significant difference between the achievement of boys compared to girls. Remember, you're going to need a p-value less than or equal to 0.05 in order to be statistically significant. What that means is that in 95% of the time, you would not get one this large if it were by chance alone. What I also wanted to find out, though, is not just do boys differ from girls in reading achievement, but do more boys fail in reading compared to girls. So I transformed my continuous variables of the reading scores into categorical variables. So first I coded my boys as 0 and the girls as 1. Then transformed as I said, the continuous reading scores into 0 as severely reading disabled if their score was at or below the 10th percentile, and then 1 meant reading disabled, the 11th to 30th percentile. And from the 31st percentile up, I classified them as normal readers. So here's the results. You can see that in grade 1, there were 12% of the boys who scored below the 10th percentile and 8% of the girls. It was about the same percentage in 3rd grade. Visually, that looks like it might be a difference, but if you go down below, you can see that the chi-square test of whether there was a difference resulted in a p-value of 0.19. So no, there was not a significant difference in the percentage of severely reading disabled boys compared to girls. When you look at the reading disabled, which is the 11th to the 30th percentile, you can see there's a much more even percentage of boys and girls at both grade levels who scored in that range. And again, the chi-square showed that there was not a significant difference. This is an example, I think, of where inferential statistics will help you to not overgeneralize what looks like a difference. Because again, if you go back to that severely reading disabled box, part of the graph, you could on visual inspection think that that meant that there was significantly more boys who failed in reading than girls. So it is inferential statistics that will answer that question for you and keep you from making a false assumption. Let me talk about when you want to look at something a bit more complex, and that was, what are the odds of a kindergarten child failing in reading, going across the grades 1 through 5, given that he either passed or failed the SRS, that he is a boy, that the kids are low income compared to full pay, and whether the age of school entrance made a difference. 0 were young for age, 1 were the kids who had fit the right age, and 2 were over age, either had been retained or had been kept back from entering. Again, I coded my dependent variable, my reading scores at each grade level, as 0, fail, if their total reading score on standardized reading test was at or below the 35th percentile, or they had been identified for Title I or LD reading. Kids who scored above the 35th percentile were coded as pass. So now let's see, what are the odds of failing in reading based on the variables of kindergarten screening score, gender, socioeconomic status, and age at school entrance. These are called odds ratios. So what's the probability of failure based on this combination of variables? You want to see an odd ratio of at least 1 time more, or two times more, in order to say that it's very significant. So immediately you notice that in the presence of all of these variables, having failed or placed in an at-risk category on the SRS made it much more highly probable that the student would fail all the way through 5th grade. Let's go down to age. Notice that age made hardly any difference in the failure rate at any grade level, none at all at 3rd to 5th, and only at 10 to 20% more in 1st or 2nd. Gender, likewise, was not an effective predictor of failure at any grade levels. But now, let's go back up to socioeconomic status. And 1st and 2nd, being of low income, did not increase by much the risk of failure. But notice in 3rd, 4th, and 5th how the risk of reading failure increased exponentially, really, for low-income kids in the presence of these other variables. Now, is that a measure of the fact that they come into kindergarten with lower scores? Well, the scores on the language subtest of the SRS were not significantly different, but we do know from longitudinal studies that low-income kids are much more likely to have academic regression over the summer because of lack of educational opportunities, and I think that that's what is reflected in these data. I want to talk about one more study. Actually, I haven't done this study yet, but these are essay ratings for our FGI scholars, and we rated them as either below average, meaning they probably need a developmental writing class as they enter college, as average, or as above average, meaning they can go into one of our advanced writing classes. The first thing you notice about this is that certainly this little group of FGI scholars doesn't follow a normal distribution. But the real question that has to be answered is it likely that the population of all college freshmen would follow a normal distribution where you'd have a smaller percentage below average, the larger percentage in the average, and then above average, a smaller percentage? Well, I think that's a question that can be debated. I know myself that I don't think it's necessarily normally distributed, but I certainly have not had the opportunity to assess that in our total population of college freshmen. So what do you do when you don't know if the population that your sample comes from is normally distributed? Well, here's the best advice I can give you. Some researchers in that case use parametric tests because they don't know that the population is not normally distributed, and parametric tests are more powerful for small samples. Other researchers use non-parametric tests because they don't know that the population is normally distributed. In fact, with small samples of less than 12, it may be impossible for the p-value ever to be less than 0.05. So, bottom line, if you're not sure whether your population is normally distributed, there's not a clear-cut answer here. I myself tend to use parametric tests in that case because they are more powerful for small samples. So here's a summary of almost everything you need to know about statistics. Use descriptive statistics to describe your sample. So your descriptive statistics will either be mean, standard deviation, and range if your variables are continuous and variables. It will be mean, percent in each category, and range if they're categorical, such as rankings. You may use correlations and contingency tables or cross breaks to also describe your sample. You can use histograms and scatter plots to picture your data. Your scatter plots will result in a correlation coefficient, which also gives information about your sample. You will use inferential statistics to test hypotheses about differences between groups or growth from pre-intervention to post-intervention. So for two groups, for example, two different kindergarten classes, maybe your last year's kindergarten class compared to this year's kindergarten class where you did an intervention that was different from last year, you would use a t-test because kindergarten children scores on something like a phonological awareness test or a reading test would be a continuous variable. So you'd either use for two groups t-tests or Mann-Whitney, depending on whether it's normally distributed or not. You would use ANOVAs or ANCOVAs for three groups or more, Crisco-Wallace or Wilcoxon if they're not normally distributed. And chi-square Fisher's exact, which is like chi-square, except it is exact p-values or odds ratios. This hopefully gives you quite a bit to think about and tentatively plan what kind of statistics you will be using with your research project. First, the descriptive statistics to describe your sample, and some tentative idea of what inferential statistics you may need.